The next control volume I have is a throttle. And this is the only control volume that I'm really okay with you memorizing, okay? The throttle. Because the throttle is like a valve. Okay? And it's going to look, we're going to draw it either like this with a circle, or we're going to draw a box with the X there, and you're going to have a flow coming in and a flow coming out, a flow coming in and a flow coming out of this valve. Okay? And we're going to use that to throttle or probably reduce the pressure or something that's going into or whatever situation we're dealing with. Okay, so let's look at how we would deal with this. Again, my control volume is going to be this thing. This is my control volume. So the change in energy of my control volume with respect to time is equal to Q dot minus W dot plus the summation of my mass flow rates in times my enthalpy in, my kinetic energy in, my potential energy in, minus the summation of my mass flow rates exiting times my enthalpy exiting, the kinetic energy exiting, and the potential energy exiting. Okay, that's what we have. Now, I'm not going to write down the typical assumptions because I think by this time you know what the typical assumptions are going to be here. This is going to be steady state, so this is going to go to 0. If I look at the throttle, I'm going to say there's no shaft or electricity needed to run it. That throttle is there the way it's always supposed to be. And so there's going to be no power applied to a throttle. In addition, the flow is going to be going through this throttle so quickly that usually is going to have no heat transfer. So we're going to have this heat transfer is going to go away. And the kinetic energy and the potential energy effects are going to be negligible. A lot of things can go away. Now, this is not always the case. There's sometimes you have a throttle that's going to have some heat transfer. But in our cases in Thermal 1, they're all going to go away. And so when this happens, you're going to end up with 0 is equal to m dot times h1 minus h2. Well, what does that mean here? M dot can't be 0. So that means that h1 minus h2 has to be 0. Okay, so we can say that 0 is equal to h1 minus h2, or that h1 equals h2. Okay, and this is what you can memorize about a throttle. I think I even put it on the equation sheet. The enthalpy coming in is equal to the enthalpy coming out. Now that's the only thing you can say, that the enthalpy coming in is equal to the enthalpy going out. You can't say the temperature coming in is equal to the temperature going out. You cannot say the pressure coming in is equal to the pressure coming out. The only thing you can say is that the enthalpy coming in is equal to the enthalpy going out. Okay? A lot of times students will say, well, everything coming in is what's equal to what's coming out. That is the exact wrong thing to do. Make sure that you understand that the enthalpy coming in is equal to the enthalpy going out. See how I repeated that 100,000 times? That's because it's very important. Students often make the mistake where they'll say, okay, coming in, whatever's coming in is going out, and that is a big, big issue. Okay, so that is a key. All right, that's a throttle. The last thing I'll talk about, I'll throw in here, the very last is a flash chamber. You will see a flash chamber from time to time in this class, and what it is a big chamber that's coming in as state 1 is going to be probably steam. Okay, it's going to be some steam of some quality. I'll say it's going to be a steam, or it's going to be a high quality liquid vapor mixture. Okay, and what we're going to do inside of this flash chamber is going to be reduce the pressure or something like that. Something's going to happen, and out this side we're going to have a saturated vapor. And coming out this side, what's going to happen is we're going to have liquid water that's going to show up here, and we're going to have saturated liquid. Okay, so a flash chamber is steam goes in there, it flashes, some of it turns into liquid water, some of it turns into saturated vapor. And then what you're going to see is what's going to come out here, you might have m.1, and you have m.2, and you have m.3. Okay, now one thing you must understand here is that m.1 has to equal m.2 plus m.3. That has to be the case. Okay, mass coming in at 1 has to equal the mass going out at 2 and 3. Excuse me. But what you need to understand is that m.2 does not equal m.3. Okay, You can't say, well, half of it's coming in at 2 and half it's leaving at 2 and half it's leaving at 3. That isn't the case. You're going to have to use the first law of thermodynamics to determine what the mass flow rate is at 2 and determine what the mass flow rate of that is at 3. And you'll see some problems like this that I'm going to assign that you can look at that. What the most common assumption, students really do a good job with the flash chambers. They're like, I can do this, I can analyze this, I can do the first law with this. But what they often do is they make this assumption that mass flow rate at 2 is the same as the mass flow rate at 3, and that really screws them up. Okay, that really screws up their problem and that's really the only error they make on this problems. Okay, so that's what we do for a flash chamber. Okay, what I'm going to do now is I want to do a couple problems for you, and then we'll be able to call this a day.